Okay, so in this video I'm going to run through the questions you need for quiz 11. There's revision from CC9, which is the calculations topic. I'm just going to split the calculations topic up and do a little bit every week to make it more manageable. And then CC16 is fuels, which is what we're currently doing at the moment. So we're going to start with the calculation questions. The first one says calculate the percentage by mass of magnesium in magnesium carbonate. To do this, you need the formula mass of magnesium. So there's only one magnesium in magnesium carbonate, and the mass of magnesium is 24. Then you need the formula mass of magnesium carbonate as a whole. Okay, so to get the formula mass, magnesium carbonate has one magnesium with a mass of 24. It's got one carbon with a mass of 12. It's got 3 oxygens, each with a mass of 16. So I'm getting this information here. I add all those numbers together, and you're asked to get the percentage by mass. So magnesium had a mass of 24, magnesium carbonate has a mass of 84, and you just get that as a percentage. It's going to be 24 divided by 84 times by 100, and our answer is 28.57. Okay, it doesn't ask for a specific number of significant figures, so I'm going to leave it as that. Down here, similar type of question. This time I'm asked about the percentage by mass of chlorine in phosphorus oxychloride, POCl3. Now pay attention here. Above, there was only one magnesium in magnesium carbonate, so I just needed the formula mass of magnesium by itself. But down here, there are 3 chlorines in phosphorus oxychloride. So I take chlorine and I multiply it by 3. So the total mass of chlorine is 106.5. So 35.5 times 3. The formula mass of the entire thing is phosphorus, which is 31, oxygen, which is 16, and then Cl3 again, which is 35.5 times 3. So the whole thing is 153.5. So that's the mass of the chlorine, 106.5, divided by the whole thing, 153.5. Again, I'm timesing that by 100, so 106.5 divided by 153.5 times by 100, and I get an answer of 69.38. And again, I'm not asked about a specific number of significant figures, so I'll leave it like that. The next page, I've got these Avogadro constant questions. So again, if you're given Avogadro's constant, you absolutely have to use it. Calculate the number of atoms you've got in 1 mole of copper iodide. So anytime we want to work out the number of molecules, number of atoms, number of ions, we take the number of moles and we multiply it by Avogadro's constant. So in this case, we've got 1 mole, so it's going to be 1 times by Avogadro's constant. So you don't actually need to do the split because obviously it just equals Avogadro's constant, okay? But they're asking you for the number of atoms. Copper iodide is not an individual atom. In copper iodide, I've got 3 atoms. I've got 1 copper and I've got 2 iodines. So I know how many copper iodides I have. I've got this number of copper iodides, but in each copper iodide, I've got 3 atoms. So I'm gonna have to times that by 3. So 6.02 times 23 times 3, and you get 1.806 by 10 to the 24. In the next question, they ask you to calculate the number of molecules. Again, they're giving me Avogadro's constant, so I know I have to use it, but this time they're giving me a number in grams. Now, if I look up here, I can't work out the number of atoms or molecules or ions using grams. I have to have moles. But luckily, with grams, I can easily find moles using G Mr. Moles triangle. So that's my triangle, G Mr. Moles. If I want to find moles, I cover it up. G divided by Mr. G, they tell me, is 0.11 grams. Divide that by Mr. So Mr is relative formula mass of CO2. They told me is 44. So I work that out, 0.11 divided by 44, and I get 2.5 by 10 to the minus 3. This is the number of moles, okay? Once I know the number of moles, if I do moles times by Avogadro's constant, I'm going to work out the number of molecules I have, which is what I'm asked about. So I'm going to do 2.5 by 10 to the minus 3 multiplied by 6.02 by 10 to the 23. So I'm multiplying that by Avogadro's constant. Oh crap, I did it wrong. 2.5 by 10 to the minus 3 times by 6.02 by 10 to the 23, and I get 1.505 by 10 to the 21. I pay attention though, it tells me to give my answer to 2 significant figures, alright, so I need to round that down to just 1.5. I'm going to leave out the 0 and the 5, and then I keep the 10 to the 21. So this doesn't count as a significant figure, so these are my 2 significant figures, and that gets me 3 marks. The next question is something very similar. Again, I'm given grams. Again, I'm asked to calculate the number of molecules. So again, first thing I'm going to do is G Mr. moles. To find moles, it's G divided by Mr. This I'm going to have to work out Mr. for myself. Okay, they tell me that oxygen is 16 and sulfur is 32, but I need to actually work it out. So the formula mass is going to be sulfur, which is 32, plus oxygen, which is 16, plus oxygen again, it's SO2, there are 2 oxygens there. So that's going to give me a formula mass of 64. So now I've got my mass, my G, I've got my Mr. 48 divided by 64 is 0.75. If I know how many moles I've got, I times my number of moles by Avogadro's constant, and my answer, 4.515 by 10 to the 23, is the number of molecules that I have. And I'm going to double check. I'm not asked to give it to a certain number of significant figures, so I'm going to leave it as it is. The last one down here, calculate the mass in grams of a hydrogen atom using the data below. Okay, so you're given 2 numbers. You're given the number 1 and you're given the number 6.2 by 10 to the 23. These are the only 2 numbers that you need to use. Okay, and to be fair, there's only a certain number of things you can do with 2 numbers. I can add them, I can divide them, I can multiply them, I can subtract them. But I'm going to be doing one of those 4 things, so you may as well give it a go. You're asked for the mass in grams of a hydrogen atom. Now we know atoms are absolutely tiny, and if you're asked for the mass in grams, I am expecting a really small number. When I say really small, I don't mean the number 1 or 2 or 3. I want my answer to be in standard form, and I want it to be by 10 to the power of minus something. Okay, because that will tell me I've got a really small answer. Standard form by 10 to the power of a minus number instead of by 10 to the power of a plus number. And I would expect this number here to be big. I would expect it to be at least over 20. Okay, that gives me a really tiny number. So what can I do to these 2 to get a small number? I'm not going to add them and I'm not going to multiply them because that's going to make them bigger. Subtracting them isn't going to be enough, so I'm going to divide. And if I'm dividing, I mean, there are 2 ways you can divide. You can put 1 at the top, and you can put this number at the bottom, or you can put this number at the top, and you can put 1 at the bottom. All right. Now, if we look at this one, this number divided by 1 is itself. This number is not a small number. This is a huge number. It's by 10 to the power of plus 23, which means there's 23 zeros going this way. The number is huge. But if I do it this way, if I put the 1 at the top, 1 divided by 6.02 by 10 to the 23, I get an answer of 1.66 by 10 to the minus 24. This number is absolutely tiny, so it fits that this would be the mass of a hydrogen atom in grams. Okay, so you're given 2 numbers, you have to use them, make it really small, you're going to divide, you're going to put the big number on the bottom, and this is what you're going to end up with. That's the end of the calculation questions for this week, so it's mostly centered on Avogadro's constant and percentage by mass. The rest of the questions are all about fuels, so probably a little bit easier. If we go look at the statements, most of the fuels are obtained from crude oil. What statement about crude oil is correct? Crude oil is a compound of different hydrocarbons. It's not a compound, okay? Crude oil is a mixture. It's got lots of different hydrocarbons together, so the answer is going to be B. It's a mixture of hydrocarbons. This one here is wrong. It contains different if they were different, they wouldn't have the same formula, okay? And crude oil is an unlimited supply of hydrocarbons. That's not correct. We know it's a finite resource. It's eventually going to run out. So the answer there is going to be B. It's a mixture of lots of different hydrocarbons. You need to separate the hydrocarbons so that they're useful. The process we use to separate them is fractional distillation. Don't just write distillation here, write fractional distillation. This next one is quite straightforward. You just need to know your uses. So kerosene is a fuel for aircrafts, and diesel oil, easier, is a fuel for cars. So you get 1 mark for each of those. My pages, sorry, are on the wrong order. And then you want to give a property. So they show you that kerosene is above diesel. They don't have to do that. You are expected to know the order. So if kerosene is above diesel, you can pick any property. So we've learned about boiling point, we've learned about viscosity, we've learned about ease of ignition. I'm going to go for boiling point, and I'm going to say prime property I'm talking about is boiling point. Remember, they're all liquid, so we're talking about their boiling point, not their melting point. They've already melted, so we're going to boil them. The property is boiling point, and I'm going to say kerosene has a lower BP, boiling point, than diesel oil. Okay, because boiling points are low at the top and they get bigger going down. Kerosene's above diesel, therefore it has a lower boiling point than diesel oil. Next page here, number 10. Properties vary from top to the bottom. Which of the following is a trend in property of the fractions obtained from the top to those obtained from the bottom? So the average number of carbon atoms in molecules present decreases. So as I'm going from the top down to the bottom, does the number of carbon atoms decrease? No, the number of carbon atoms gets bigger as you go from the top down to the bottom. Does the ease of ignition increase? No, it's harder to light them as you go from the top to the bottom. So bitumen's like a thick, sticky liquid. It's much harder to light than something like a gas, like we would use in a Bunsen burner. The boiling points decrease. That's also incorrect. The boiling points are getting bigger as you go down. So the viscosities increase. That is correct. So viscosity, if something's viscous, it's hard to pour. It's much harder to pour bitumen, a thick, sticky liquid, than something like petrol, which is a nice thin liquid. So viscosity is increasing. And the next one is a graph, explain the trend, and it says explain the pattern, so not just state the pattern. So the pattern you can see is that as the number of carbon atoms in a molecule increases, so I'm going from 1 carbon atom at the start to 9 at the end, the boiling point increases. So you're asked to explain that pattern. So the trend that I'm seeing is the number of carbons increase, the boiling point also increases, okay? But your explanation, these are all simple molecules. So hydrocarbons are simple molecules, and when you're talking about boiling a simple molecule, you're talking about overcoming intermolecular forces. Now they all have intermolecular forces, but the bigger the molecule, the stronger those intermolecular forces are going to be. So you can say the intermolecular forces get stronger as the molecules get bigger. Because those forces are getting stronger, the boiling point is increasing. And that's it for this week.